Okay, this video uses multiple regression to develop useful models for data that is either nonlinear or has interactions between the variables. We'll begin with nonlinear models and start with the most common, polynomials. This family of functions includes parabolas and other functions with higher powers of x. These models are relatively easy to create and analyze because we're so familiar with them, especially parabolas. They were probably the first nonlinear function that you studied in your math classes, and they'll be the first model that we look at here. The process of creating the polynomial model in your computer is pretty straightforward. Let's suppose that we already have our data set containing a column of data for the x variable. Then we just need to add a new column in our spreadsheet called x squared that contains the square of all the x values. And if we want, then we could add another column called x cubed containing the cube values, and so on, to any power of x that we see fit. Let's return to a dataset that I showed you in the video on simple linear regression assumptions. The y variable is sales, and the x variable is called months, for months of experience. The original reason I showed this data set was that it violates the straight line model assumption of simple linear regression. And the scatter plot shows a nonlinear trend in the data. But now we're going to use a nonlinear polynomial model instead of a straight line. We're going to begin by using a quadratic model to find the best fit parabola through the data. If the x variable is months, then we just need to add a column called months squared that contains the square of each x value. And when we do the multiple regression using the two x variables, we get a quadratic or parabolic model for the data. The scatter plot shows the data with the best fit parabola, and it looks like it fits the data quite well. Before going on, I want to quickly remind you of the regression output for the straight line model. Notice that a straight line by itself is already significant, and it has a pretty good fit. And the scatter plot did show that y values tend to rise as x values increase. But the problem isn't that the y values, the problem is that the y values don't rise linearly. And we can see that in the residual plot. And that is our primary clue that a straight line model isn't appropriate, even though it is statistically significant. Here's the regression output for the quadratic model. The main question is whether or not the parabola is significantly better than a straight line. And there is one number in the output that tells us the answer. It is the p-value of the x squared term. We can see that this term is significant, and so the parabola model is significantly better than the straight line model. You need to remember the interpretation of the t-test from the multiple regression videos. If you already have the other variables, then does adding this variable significantly improve the model? Or in this particular situation, if you already have a straight line, then does adding the x squared term to make a parabola significantly improve the model? And yes, it does. It's also worth noting that the fit is noticeably better than the straight line fit. And we can also find the residuals for the quadratic model and see there is nothing wrong with them. If we had still seen a curved trend in the residual plot, then we would consider the possibility that the parabolic function isn't curved enough for our data and try higher powers of x, like a cubic or quartic polynomial. But this plot looks fine, so the quadratic model looks like a winner. But there's nothing to stop us from trying a cubic model, so let's see what would happen. This time I added the third power, or cube of x, into the spreadsheet and redid the regression. There are a couple of interesting things in this output. The first is the p-value of the x cubed variable. It is not significant, so we may conclude that the cubic model offers no significant improvement over the quadratic model. Furthermore, when we look at the best fit quadratic next to the best fit cubic, we see that there is practically no difference between them, and the fit is virtually the same as before. This also confirms that the cubic model provides no added benefit. However, the cubic model is very significantly related to sales. And now that we notice it, the variables for x and x squared are no longer significant. What's going on here? Well, we've seen this kind of contradiction before. This is our old friend multicollinearity again. When you think about it, it's quite natural that x squared, and x cubed are all strongly correlated with each other in this data set. When x increases, then automatically so does x squared and x cubed. So not only does x cubed not significantly improve our model, it brings a lot of unwanted multicollinearity into the model as well. For all these reasons and more, we conclude that the quadratic model is superior to the cubic model and straight line model, and use that one going forward. After we settle on the best model, we should always be prepared to analyze the function that we've chosen. In our sales example, we end up with this quadratic function as the best fit curve. This is a parabola with a negative coefficient in front of the squared term, so it opens downward and has a maximum point. We can use basic facts about the vertex point of a parabola or a little calculus to find that the maximum point is approximately where x is equal to 92. That implies that new workers improve their sales quickly at first, more slowly as time goes on. And that is very accurate to what we usually see in real life. But then it gets a little ridiculous. The parabola reaches its maximum point at 92 months and then begins to decrease. That suggests that workers reach their maximum expected sales at 92 months. And after this point in their career, any additional experience will decrease their expected sales. Furthermore, their expected sales will decrease faster the longer they work. Now, it isn't completely unreasonable in the real world for certain workers to experience some decline as they get complacent about their work or simply get old. However, the implications of this graph are pretty extreme. Anyway, we have to go back and look at our data set to put this in perspective. Almost all of our data points have x values less than 90. Therefore, this should be the interval where our model works best, where most of the points are. And this is where our data is all about, showing us the rate at which less experienced workers are improving. Even though the best fit parabola implies that workers reach their peak after 92 months and then begin to decline, common sense tells us that this probably isn't true. And there aren't enough data points out there to justify it. It would be unreasonable to use this model with more experienced workers. But we don't seem to have to worry about that since very few people stay at this job long enough to have that much experience. Just remember that your model may work well enough within the interval where your model may work well enough within the interval where most of your data points lie, but you should be wary about extrapolating beyond that. Now I want to remind you what polynomials look like in case you happen to come across a data set with these properties. The degree of a polynomial is its highest power of x. So this first graph that you see has degree equal to 2, so it's quadratic. And the graph has the shape of a parabola. The number of critical points that a polynomial can have is at most the degree minus 1. So a degree 2 polynomial has one critical value. In this case, it's a minimum. A degree 3 polynomial can have two critical values, a maximum and a minimum. A degree 4 polynomial can have three critical values, and so on. If your data set sort of looks like one of these graphs, i.e. it has hills and valleys, then you can make a good initial guess at what kind of polynomial to try. And although we're not going to talk much about other nonlinear functions, any function could be fit to the data. For example, the sales versus experience data from the last example could have been modeled by a square root function instead of a parabola. There is one more nonlinear curve that I want to look at because of its importance to financial mathematics. That is the exponential curve. The basic exponential function has this form where beta 0 is the intercept and beta 1 is called the base. This function may seem like something totally new at first glance, but it's actually very simple if we think about logarithms. In particular, if we take the natural log of both sides of the equation and apply the rules of logarithms, then we end up with the natural log of y being equal to a nice, simple, straight line. Here's an example of exponential data that I made up. The y variable is debt, and the x variable is year, beginning in 1981. It is very common but not necessary for the x variable to be related to time. To fit an exponential curve to this data set, we just need to replace y, or debt, with the natural log of y. Looking at the data after this transformation, we see a pretty clear straight line with this equation. I'm not going to look at the regression output. I think it's pretty safe to say that just by looking at this that it's going to be significant. But I'm going to focus on this best fit line equation to see what it means. So here's the best fit line equation from the last slide. And remember that we got this equation after we had transformed y into the natural log of y, so let's put that back into the equation. Now it's just a matter of applying the rules of exponents and logarithms. The next step is to raise both sides of the equation to the power e. That cancels with the ln on the left side, so we just end up with y. Next, we can separate the right side of the equation like this. And finally, we calculate the exponents. E to the power minus 143 becomes this incredibly tiny number. And e to the power 0.079 becomes 1.0825. This base is really important to the interpretation of the exponential curve. All exponential curves are the result of constant percent growth each time that x increases by 1. And the base of 1.0825 means that y, or debt, is growing by 8.25% per year. And one last note, the intercept of 7.4 times 10 to the minus 63 might seem strange because of how small it is, but just keep in mind that this data set began with x equal to the year 1981, or as the computer understands it, 1981. So if we trace this back all the way back to where x equals 0, then it starts to make sense that the intercept is barely greater than 0. All right, that's all I want to say about nonlinear models for now. The next main idea is interaction variables. We briefly bumped into interactions back when we studied two-way ANOVA, and the basic idea remains the same. One x variable's relationship with y depends on the value of the other x variable. In regression, interaction variables are easy to make, but much less easy to interpret. We can create an interaction variable by taking any two x variables and multiplying them together. And this is the simplest possible interaction model. It has the variables x1, x2, and their interaction. Here's a nice example of a data set with interaction. The y variable is sales for some product, and the x variables are its price and advertising expense. And here is a plot of sales versus price. To help see the effect of interaction, I've color-coded the points. The first 12 points all have an advertising value equal to 50, and I've colored them in blue. The last 12 points all have an advertising expenditure of 100, and I've colored them in red. The blue dots are more or less in a straight line, and so are the red dots. But the important thing is that these two dots also seem to have different slopes, and that signals the presence of an interaction. In order to add the interaction variable into our model, we just need to add a column where we've multiplied the two x variables together. And that will be our interaction variable. Here is the regression output for the model. The interaction variable is very significant, so it definitely belongs in the model. But the trick now is how to make sense of the model, so I'm going to focus on the best fit coefficients we see here. Try to figure out what they mean. So here is the best fit curve equation with the interaction. First, I'm going to find the equations of the two lines we saw in the scatter plot. Let's begin with the blue points where advertising is equal to 50. If we set A equal to 50 in the equation, then the relationship between price and sales simplifies to this equation. Let's now move on to the red points where advertising is equal to 100. If we set A equal to 100, then the relationship becomes this equation. So the effect of price on sales depends on the value of advertising. When advertising is equal to 50, then the effect of raising price by $1 is a decrease of $1.29 in sales. However, when advertising is equal to 100, the effect of raising price by $1 is a decrease of $433 in sales. That's quite different. We can also ask hypothetical questions like this. What price would make advertising have zero effect on sales? So let's put everything without the variable A out in front as the intercept, and then factor A out of everything else so that it looks like a straight line equation where this bracket is the intercept and this bracket is the slope of A. Notice how the slope of A is affected by the value of P because of the interaction. Next, if A has no effect on sales, then slope must be equal to 0. And that means that price must be equal to 3.24. We can also ask the same kind of question, but this time focus on the relationship or slope of price. This time we'll put everything without the variable p out in front as the intercept, and then factor p out of the rest. So this bracket is the intercept, and this bracket is the slope of p. And if the slope is equal to 0, then advertising must be equal to 28.78. Let's look at another example. This model is entirely made up, but we can analyze it to see how it works. In this example, the y variable is sales, and the x variables are customers' salary, S, age, A. We can see that salary has a quadratic relationship to sales, as well as interacting with age. Furthermore, the squared term of salary also interacts with age. This is a much messier equation, but we can still make some sense out of it. Let's first look at the relationship between age and sales. If we move all the terms without the variable a out in front as the intercept, and then factor a out of the rest, then we'll get this expression. It's still pretty complicated though, so we can apply what is called the spotlight method. This means we'll plug in a range of the most common salaries to see how the slope of age changes. And I put the results in a table down here. These numbers are all negative, so it seems that increasing age would always lead to decreasing expected sales. Furthermore, the slope of age is decreasing faster as salary gets larger. We can look also at the relationship between salary and sales. Since salary has a quadratic relationship with sales, we can ask some interesting questions, like what salary would maximize sales for a 40-year-old customer? This time we arrange the terms into 3 basic groups: those without S, those with S, and those with S squared. After factoring, this looks like a basic quadratic equation, or ax squared plus bx plus c. But all the coefficients depend on age. If age is equal to 40, then the leading coefficient will be negative, and the parabola will have a maximum point at its vertex. And the vertex is where salary, S, is equal to 50. So a salary equal to 50 would maximize sales for a 40-year-old. Let's look at one last example. This time the y variable sales depends on price, advertising, and supply. And the relationship is very messy. Not only are there several two-way interactions, but there's also a three-way interaction at the end of the equation. These are very rare in real-life data, but let's analyze this weird equation anyway. Let's try focusing on the relationship between price and sales. So we'll put every term without the variable p out in front as the intercept, and then factor p out of the rest. Now we can see what a three-way interaction does. The relationship or slope for price depends not only on the values of A and S, but also on their interaction. And that's amazingly convoluted. Just about the only way we can make sense of this is to apply the spotlight method. Here I've created an array of noteworthy values for advertising and supply. When we plug in each combination of values, we get the following slopes for price. These numbers are all negative, so it seems that a price increase always leads to a decrease in expected sales. However, the decrease is much smaller when advertising and supply are both small. On the other hand, the decrease is much larger when advertising and supply are both large. Finally, we've reached the output for the 3 questions at the end. This first example is a data set that might be nonlinear. On the right, I've shown the regression output for the linear model and the quadratic model. This will be used in problem number 1. Next, in problem number 2, we have transformed y into the natural log of y and gotten this best fit line. And last, in number 3, I want you to consider this interaction model. Good luck with that, and check out the next video.